Have you ever just clicked a button on your computer and wondered, what is actually happening in there? How does this hunk of metal and silicon take a simple thought and turn it into something real on the screen? Well, that's what we're going to do right now. We are pulling back the curtain to demystify how computers really think.
It all boils down to this one kind of wild question. How do you tell a rock to think? Because at its core, that's all a computer really is, a very, very sophisticated rock, sand, really, that we've figured out how to teach. And cracking that problem is what kicked off the entire digital world.
So here's the game plan. We're going to start with the recipe a computer follows. Then we'll look at the actual machine that does all the work. From there, we'll get into how we speak its language, how it makes choices on its own, and finally, how it keeps all its data from turning into a total mess.
All right, first up, the recipe. See, before any machine can do anything, it needs a plan, a really clear step-by-step plan. And in the world of computers, we call that plan an algorithm.
Honestly, the best way to wrap your head around an algorithm is to think of it just like a recipe for baking a cake. You've got your ingredients, right? That's your input. Then you have a very specific set of instructions to follow. And if you follow them perfectly, you get a cake, your output. Every single thing your computer does, no matter how big or small, starts with one of these recipes.
Now, this whole idea of building machines that can follow recipes, it's ancient. It goes all the way back to tools like the abacus. But the real game changer came in the 1800s. A guy named Charles Babbage designed something called the analytical engine, basically the first blueprint for a machine you could actually program. But it was his partner, Ada Lovelace, who really saw the future. She wrote the world's first algorithm for it, realizing these things could do way more than just crunch numbers. Okay, so we've got the recipe, the algorithm. But brilliant ideas are just ideas, right? You need a physical machine for them to run on. You need a blueprint to turn that abstract logic into actual, real-world action.
And that blueprint arrived in 1945 from a genius named John von Neumann. His whole design, his architecture, was absolutely revolutionary for one simple reason. It stored both the program's instructions, the recipe, and the data it was working on, the ingredients, in the exact same memory. That one idea made computers incredibly flexible. And guess what? It's the same basic design that pretty much every computer, including the one you're watching this on, still uses today.
So this design has three key parts. You've got the CPU, which is the brain of the whole operation. Then you have memory, or RAM, which is kind of like the brain's short-term scratch pad. And finally, you have your input and output devices, your keyboard, your mouse, your screen, which is how we talk to the machine and how it talks back to us.
So how does this brain actually work? Well, it just runs this relentless four-step cycle over and over billions of times a second. First, it fetches an instruction from memory. Next, it decodes it to figure out what it's supposed to do. Then it executes the command, and finally, it stores the result. Fetch, decode, execute, store. That is the fundamental heartbeat of every single computer on the planet. Okay, so we have our recipe and we have our machine. The big question now is, how do we get that recipe into the machine? To do that, we have to learn to speak its language.
See, deep down, the CPU only understands one thing: electricity. That's either on or off. We represent this with ones and zeros, or binary. That's machine language. It's super fast, but for us humans, it's a nightmare to try and write. So to fix that, we invented high-level languages like Python or C. They use words that look a lot more like English, which makes writing our recipes way, way easier.
Now for our examples, we're going to be using the language C. People call it a middle-level language because it's kind of the perfect bridge. It's easy enough for us to read and write, but it also gives the programmer really powerful, direct control over the computer's hardware. It's the best of both worlds, really.
So now we've got our language. We can talk to the machine. But a recipe that just goes in a straight line isn't all that smart. The real power, the real magic, happens when we teach a computer how to make choices.
And we do that with something called conditional statements. Basically, they let a program ask a simple true or false question and then do different things based on the answer. It's like giving the program a fork in the road, which lets it adapt and react to whatever's happening.
Let's look at a really simple if-else statement in C to see how this works. The code asks a question. If I take this number and divide it by 2, is the remainder 0? If the answer to that is true, it prints the word even. Else, meaning if the answer is false, it prints odd. It's so simple, but it's an incredibly powerful piece of logic.
And we can even chain these choices together to handle more complicated stuff. We call this an if-else-if ladder.
The program just goes down the list, testing each condition one by one. Is the score 90 or more? No? Okay. Else if it's 80 or more? No? And it just keeps going down the ladder until it gets a true. This is exactly how a program can make complex decisions, like figuring out what grade you get on a test.
So our program can follow instructions, and it can make decisions. But most useful programs need to work with huge collections of information, not just one thing at a time. So how does a computer keep all of that organized? Well, one of the most fundamental tools for this job is the array. The best way to picture an array is just like a row of numbered mailboxes. It's a list of items, all the same type, like all numbers or all names, and they're all stored right next to each other in memory. And since every mailbox has a unique number or an index, you always know exactly where to find every single piece of data.
And here's the really clever bit. Because all the items in that array are stored contiguously, literally right next to each other, the computer can find any one of them almost instantly. It knows where the array starts, and it knows how big each item is. So it can do some super fast math to pinpoint the exact memory address of anything in that list. No searching required. This is what makes arrays so fast and so efficient.
And this brings us right back around to where we started. From the very beginning, pioneers like Ada Lovelace knew that these machines, these incredible recipe followers, were not just giant calculators. As she wrote way back in 1843, they could be taught to compose elaborate and scientific pieces of music, that they could handle any kind of symbol or idea we could dream up.
Her vision has totally become our reality. We've gone from teaching a rock how to count to teaching it how to create art. And that just leaves us with one final, huge question. What incredible new ideas will we teach computers to think about next?